I'm a retired chemical engineer. I went down a different path than burning cattle manure in my career. And I'm speaking to you from my home office out here south of Austin near Driftwood. And I do want to thank the Society for the opportunity to speak. I usually only have at most, the sometimes grudging attendance of my family when I present one of my PowerPoints. And my PowerPoints are famous within my clan, or infamous. So I do appreciate this venue. When I told Mike that I was working on yet another PowerPoint for my 3 grandsons, ages 12 through 14, a presentation on the 2 solar eclipses of 2023 and 2024, one annular and one a total, the second one being a total. And that would be a presentation that I was willing to share with this group. I expected possibly to be taken up on that offer a year or 2 down the road, closer to the 2 events. But here we are. I hope this talk will not be too elementary for this group. From what I've been listening to the proceedings of this meeting, I think it might be. But I hope that everybody learns something new about eclipses and be refreshed on existing knowledge that you already have. I've chosen Smokey and the Bandit as my names for the 2 eclipses. And this is for a reason beyond just catchiness of that name for the adolescent boy. And I'll explain that later. These eclipses will each be within reach of all of us who live in Central Texas. In fact, you could eventually tell your grandkids that you saw both eclipses from the exact same spot back in 23, 24. Better yet, to take your grandkids to see the events for themselves so they can tell their grandkids. Now, see, I haven't shared gotten into.
Yeah, we've got your screen. You just
I need to get into slideshow mode, Donna.
There you go.
Now you see it.
Beautiful.
Okay. As to topics or agenda, and we can be flexible on this, I intended to begin with some short histories of notable solar eclipses and human response to them, going back as far as 5,000 years in recorded history, and even further than that in speculative history. Then I wanted to actually cover the main topic of the presentation, the Texas two-step, Smokey and the Bandit, what, where, and when. And of course, the event duration of those events, of the annularity and the totality, depending on exactly where you are. Next, I would plan to discuss the total versus annular versus hybrid eclipses, their causes, their relative frequencies, and modeling and prediction of them. Also, I wanted to discuss in a limited way the mathematical modeling and prediction of eclipses, which I'm into. Not that you would ever want to do that, given all the information available on the internet, but because it provides insight into the phenomenon themselves. And then I intended to conclude on experiencing a solar eclipse, especially for the non-astronomer, such as I am, who is not in possession of all the sophisticated equipment and gear that I've been hearing about. I hope that will be fun and inspiring as to ways to involve your kiddos in eclipse watching without actually looking up. My grandfather told me that you don't have to climb a telephone pole in order to figure out how tall it is. And that's the idea behind this last topic. As we go along, please note slide numbers. Hopefully I have them on every slide to facilitate my responses to your questions during the Q&A portion. Q&A is also for your comments. I would appreciate it. Now, I have quite a lengthy slide deck. We can modify it as necessary. The evening is progressing onward here, but my goal was to finish in an hour or so and then open it up for questions. I can only do that if I stick to a script that I have prepared for my grandkids and move along with some pace, as they say. So buckle up for some PowerPoint. Let me begin appropriately with death by PowerPoint. Not really, I'm not going to cover actually anything on this slide. I just brought it up for a purpose to emphasize again that I am not an astronomer. I'm certainly not a field or observational astronomer, even as a hobby. Mathematical astronomy is an enthusiasm that I have, but not the kind of astronomy with telescopes and cameras. But one of my actual hobbies in retirement is the creation of PowerPoint presentations. This hobby is the subject of some eye rolling within my family, to be sure. But I consider this hobby no different than woodworking. In fact, I think of it as word working. But they're right, there's some OCD at work in what I do. As I read scientific, mathematical, and historical literature, I sometimes am just compelled to make a related PowerPoint. A few years back, I got interested in the study of the ancient Greeks' eclipse prediction mechanism, which Kurt presented to you a few months back, the Antikythera mechanism, and that got my interest into solar eclipses. And so here I am tonight with this presentation. Some snippets from my other presentations based on interest are shown here right now. I hope my grandkids will fully appreciate this work at some point, and I hope they're watching on YouTube right now. As I began to decide just where to start with a history of solar eclipses, I came to think about early prehistory, say 1,000,000 BC. I pictured a group of hominids out there on the savannah on a cloudless day. They are looking down, focused on gathering their sustenance. Slowly, the sky becomes dark. They don't even look up at first, and then they are compelled to. What went through their minds in those several minutes that the sun was totally obscured by the moon? It gave me a shudder to think about it. Now this got me to thinking about what the very first solar eclipses might have looked like, not 1,000,000 years ago, but 4 billion years ago. But first you have to consider what the Earth did not always have a moon. And there has to be some speculation involved about the physical situation after our planet did get its moon. All theories of lunar formation place the moon much nearer to the Earth after its formation than it is today. So with the young moon maybe 15 times larger than the sun in the sky because of its nearness, and maybe only at the tender age of 21 years old, according to one theory at least, the so-called magnitude of the eclipses produced would have been very large to produce a total blackout for many minutes. But what about the frequency of eclipses? You may not know it, but lunar formation is still up in the air. The theories are still being hashed back and forth. The latest theory, which I like very much, is the brainchild of a team led by Saros Stewart of UC Davis. Here's her picture here. And so in recognition of her and also of Women's History Month, which March is, let's look at her theory, at least one scenario of her hypothesis. Her theory involves the same so-called giant collision, which we were all taught in school, but now thought to be of such tremendous energy that the prototype Earth was almost totally vaporized, except possibly for its core, forming a vast cloud of gaseous rock with vaporized minerals like carbonates and silicates, if you can imagine. The impacting body itself was also largely vaporized, and everything got mixed up in the cloud. It was also a glancing blow like a squib kick in football, with much angular momentum imparted and possibly an extreme tilt relative to the plane of the orbit around the sun, given to this fast rotating cloud. The geometry shown there at the bottom is thought to have been a biconcave disk called a synesta. You can think of it like a round jelly donut, which has been thumbed in top and bottom at its centers. As this synesta cooled, which it did by radiation back into space, the moon formed inside the cloud. Thus, the moon had a chemical composition almost identical to that of the mantle of the present day Earth. The present day Earth being the mixture of the prototype Earth and the impacting body. In effect, the moon was formed inside the Earth and got left behind as the Earth cooled, then condensed and shrank. The compositions of the moon and the present day mantle of the Earth are very similar. And this is very significant in support of Dr. Stewart's theory. Some of the older theories cannot explain the similarity in the composition between Earth mantle and moon, which the Apollo moon missions have shown to be the case. Now, one possible configuration of the early moon system after the smoke cleared, so to speak, is shown here. If this scenario was in fact the reality, then it's at the time of the year which I've shown here, with the Earth position relative to the sun, a solar eclipse would not have been possible. The orbital plane of the moon, tilted over as it was as a result of the impact, is almost at right angles to the sun. So the moon could not be in line of sight of the sun to cause eclipse. Now, a few months earlier or a few months later in the orbit, Earth's orbit, there would be times when the extreme solar eclipses that I mentioned could be possible, if you can imagine that. Moving back 90 degrees or forward 90 degrees in the orbit I've shown here. This lunar formation theory is still under review, and the researchers are working to finalize the mechanisms whereby the present day Earth-Moon system evolved from this possibly very different initial system. And I say possibly because Dr. Stewart emphasized to me when I talked to her about this, that the finalized possibilities may not turn out to be as drastic as I've shown here. Okay, let's get back into human history. And this slide shows what may be, just may be, the oldest known image of an eclipse. This is a stone carving at a Neolithic burial site in Ireland. The site itself has been dated to about 3,300 BCE. One researcher claims to have modeled the occurrence of an eclipse, solar eclipse, in November of 3340 BCE, which he relates to the carving. But I've been unable to find confirmation of his claim. And also, I think it's speculative to presume that these Stone Agers carved an eclipse that they have witnessed. But if not, what else could possibly be represented here? You think about it. If it is an eclipse, then they had a very remarkable insight into the phenomenon. One orb passing over another. And are those daytime stars above the sun visible during the eclipse? It might be that this is truly a historical recording from a nominally prehistoric era. I'll let you decide. The Chinese are now thought to have made the first written record of a solar eclipse in June of 1302 BCE. They etched it on the back of a tortoise shell. It reads, "Three flames ate the sun, and big stars were seen." It's easy to imagine that the three flames were coronal streamers from the sun highlighted by the eclipse. In 1223 BCE, according to revised scholarship, the Mesopotamians inscribed their witness of a solar eclipse on a clay tablet called a cuneiform. They noted that the sun was put to shame, a pretty apt description of a total solar eclipse. These Middle Easterners and their successors, the Babylonians, began the process of recording astronomical events with the aim of understanding the periodicities involved. The Babylonian philosopher astronomers, the Chaldeans, had worked out the basic 18-year period of recurrence of eclipses, the so-called Saros. Hello? This is the Saros Cycle. And they had worked this out no later than the 8th century BC. I'm hearing some noise. I don't know.
They muted.
So, a summary of what the Babylonians discovered is stated here. This is the Saros cycle that they discovered all those many years ago. Any eclipse witnessed at a given Earth longitude has a strong possibility of recurring exactly 223 lunar months, about almost exactly 18 calendar years later, somewhere on Earth. And every 3 times the Saros cycle, every 3 times 18 or 54 years, a recurrence is probable near the same longitude as 54 years earlier. And I'll get more into why that is later on if we have time. Okay, the ancient Greeks and the Persians, we're now into the about the 5th century BCE, were often engaged in war with each other or between themselves or with others. And the world's first true historians, which were Herodotus and Thucydides, recorded several instances in their writings where either lunar or solar eclipses were a source of fear or awe or divination, that is omens, to those engaged in battle. In May of 585 BCE, the armies of Persia and Lydia were engaged in battle in Anatolia, but they were so awestruck by total eclipse that an immediate ceasefire was called and terms of peace were negotiated. It is said that sometime before his invasion of Greece in 480 BCE, the great king Xerxes of Persia witnessed a solar eclipse and asked his magi, what did it portend? The magi told him it was a good omen for him and a bad one for the Greeks. Well, that turned out to be bum advice, because in the long run of the Second Greco-Persian War, the Greeks gave Xerxes a very bad time. And this story is probably apocryphal, since the only likely total solar eclipse occurred 2 years after his invasion in 478 BCE. Perhaps the sky was darkened to Xerxes by some other astronomical event, such as a sandstorm or something else, or maybe even a partial eclipse, which occurred in Persia in October of 480. In August of 431 BCE, the famous Athenian general, statesman, and orator Pericles had to use all of his powers of speech and his use of visual aids to put his troops and sailors at ease upon witnessing an eclipse. Now we get into the great age of Greek astronomy and the Greek astronomer Hipparchus. You've all heard of him, I'm sure. It is agreed that the solar eclipse of March 14th, 190 BCE, which is the year minus 189 in astronomical reckoning, afforded Hipparchus with the data he needed to make a reckoning of the distance to the moon. The eclipse that he saw was a total one in the Hellespont on the Dardanelles, while observers in Alexandria, Egypt, to the south across the Mediterranean, down here, saw a maximum obscuration of the sun of 80%. The fact that the eclipse was total in the Hellespont and only partial in Alexandria is an example of astronomical parallax, as you all know. Now, Hipparchus knew that the moon and the sun each present an angular size of about a half a degree of arc in the sky. So from this fact and other knowledge, he deduced that the distance to the moon was about 77 times the radius of the Earth, give or take. And the actual distance is about 60 times the radius of the Earth. So his result was pretty remarkable. Now, I found myself compelled to understand exactly what he did, so I reproduced his calculations using data that I thought he would probably have access to. And I don't want to go into that tonight, into the mathematics or the simple geometry involved. But I did discover that he had to know three things apart from the fact that the sun was 80% obscured in Alexandria in order to make his calculation. Focus on the three boxes shaded in green with the numbers. Number one, he had to know, at least in terms of the radius of the Earth, the surface distance between the Hellespont and Alexandria, H and A on this globe. This was about 9 degrees of latitude differential, since the Greeks, from measurements of position of their North Star, knew the latitudes of all their cities. That 9 degrees of latitude difference implies that the two cities were 0.1571 times the Earth radius apart. So he got that part. Number two, he had to know the declination of the Earth towards the sun on the date in question. The Greeks knew that the declination changed throughout the seasons in a regular repeating fashion. They knew this in spite of the fact that they assumed the sun orbited the Earth and not vice versa. So Hipparchus knew that the declination was about 3 degrees on this date near the spring equinox. Remember, we're talking March 14th. And you'll recall at the equinoxes, the declination is 0 degrees. Number three, and finally, he had to have had a measurement of the normal angular size of the sun in the sky. As we said, this was about 0.5 degrees. And so from that and 80% obscuration, he knew that the angle of what he could see, or what the people in Alexandria could see, was 80% of that, or 0.1 degrees. This very acute angle was the key to his calculation. I show up here at the top that the Greeks had fashioned by this time rudimentary instruments for measuring elevational positions and sizes of objects in the sky. And these were called diopters. Bottom line down here, I calculated the moon was 69 Earth radii distance, which is even closer than what the reference gave me, what was claimed to be his calculation. 69 is only 13% greater than the actual relative distance of the moon. This is amazing to me that they did this that far back. This slide is just an aside. I found to my glee, as I was making my calculations, that there are triangle calculational apps to fully calculate the angles and lengths of sides of the triangle on the internet if you enter sufficient information. This is very useful for resolving scaling triangles with highly acute angles like I used shown on the previous slide. Okay, this also is a sidebar that is more directly related to astronomy. 2,500 years ago, the so-called North Star, Polaris, Polaris was not the Greeks' North Star because of the slow precession of the Earth's rotational axis, which is illustrated by this top here. But actually the Earth is precessing on its axis one revolution every 26,000 years. Very slow wobbling, like a toy top in ultra slow motion. Therefore, the positions of the stars change to Earth's observers, as you know. And this wobble results from the fact that the Earth is not a sphere, but a flattened one due to the effects of its rotation. It's an oblate spheroid, not a sphere. Back in the day of Hipparchus, the true north was probably one of the stars in the cup of Ursa Minor. We think it was Kochab. Did I pronounce that right? But that was their likely North Star. You see here in blue where Ursa Major and Ursa Minor are today, where they were back in 500 BC. I want to briefly mention a couple of other famous Greek astronomer mathematicians that are not directly associated with solar eclipses, but did some remarkable work. First, Arithmetise of Tyrini. He was also the librarian at the Great Library of Alexandria. He calculated the circumference of the Earth with remarkable accuracy in the late 3rd century BCE. His results were 24,000 miles to 29,000 miles, pretty close, depending on various modern understandings of the actual units of length that he used. He used a unit of length called stadia, and we don't know exactly how far that was, but we think it was would result in the range shown here. His method, well, he knew the surface distance, the actual surface distance in miles or stadia between two cities in Egypt, and he knew the lengths of shadows cast at high noon in each city on the same day. If one assumes that the Earth is spherical, then from this knowledge, it is a simple matter to calculate the circumference of that sphere. Might add a historical note that the later great astronomer Ptolemy recalculated this and severely underestimated the circumference of the Earth. And this would later give a false hope to Columbus as he sailed for the Indies. Aristarchus of Samos, he actually preceded Eratosthenes, who in turn had predated Hipparchus. Aristarchus, sometime in the early 3rd century BCE, worked out an extremely accurate method for estimating the distance to the moon using observation of a lunar eclipse, not a solar eclipse. The Greeks knew the time that it took for the moon to complete a full orbit around the Earth, 27 and a little more days to make a full orbit. Aristarchus reasoned that if he measured the time it took for a given point on the moon to move through the Earth's umbral shadow during the lunar eclipse, that he could calculate the velocity of the moon in terms of the Earth diameter or Earth's radius. Assuming that the moon's velocity was constant and its orbit circular, he then calculated the distance of a full lunar orbit, and from that he found the distance to the moon. Now, he may have actually just worked out this method for others to implement, or he may have made the measurements himself. We don't know for sure, but it is reported that the result from this method was spot on and perfect, 60 times Earth radii to the moon. Here we have talk about crucifixion of Jesus. In Jerusalem, in Roman Judea, they experienced a total solar eclipse in the afternoon of November the 24th in the year 29 of the Common Era. This was a short eclipse with less than 2 minutes of totality. If one allows the writers of the gospel a little literary license to write that the sky was darkened for hours, as they did write, after the crucifixion of Christ, then some historians mark this November date as the date of the crucifixion. It occurred to me that if they are right in this, this would place Easter actually closer to Christmas than to Easter. But actually, I think what they probably wrote about was a severe storm and sandstorm, which obscured the sun. But that's just my opinion. Another famous solar eclipse was King Henry of England's eclipse in August of 1133. Some historians of this period believe that this event agitated the hearts of men and threw England into civil war following the death of this king. From a scientific viewpoint, the eclipse of May 29, 1919, which you've all heard about, must be the most famous total eclipse of the sun ever. This is Einstein's eclipse. This was a few years after Einstein had revealed the general theory of relativity. And examples of proof of that theory were solved. One of them involved mercury, and another one involved gravitational lensing, which is what I'm depicting here. The one prediction of the theory was that if starlight, if passing close enough to the sun, would be deflected by the warpage of space-time. This effect is known as gravitational lensing. As shown here, this displaces the actual position of the star to an apparent position to observers who can see it, but you can only see this during a total eclipse of the sun. And that's what photographic evidence was taken on an expedition led by Arthur Eddington, a famous physicist in England, and others. They led an expedition to 2 locations. You can see the eclipse map up here and see that this was a very lengthy eclipse, 6 minutes and 51 seconds. That's long duration of totality for an eclipse. But they set up stations both in South America and off the coast of Africa to photograph this thing, photograph the apparent positions of the stars, or the actual positions of the stars. I'm sorry, the apparent positions of the stars during eclipse when they would be deflected. Their photographic proof and the analysis that they did was in dispute for a number of years, but it finally won out, as we all know. I was amused by the newspaper headlines shown, some of which are shown over here. Nobody need worry. about the star displacements. That's sounds like some of the stuff we hear on the news today. Or maybe we hear more of everybody needs to work. I don't know which. I mean, there is so much information and some disinformation actually on the internet about eclipses to allow you to spend all of your time just reading about it. And here are some of the sites that I have relied on. I particularly recommend any of the NASA websites. Just Google NASA and Eclipse and you'll be there. NASA's stuff is freely available, extremely well done. Okay, at last, we get to the Texas two-step. The events to occur on October 14th of 2023, an annular eclipse of the sun, and on April 8th, 2024, a total eclipse of the sun. This will be a rare opportunity for Central Texas. I found a statement on the internet that a total eclipse occurs on the average only once every 300 to 400 years in a given spot or area. So you figure the probability of seeing two effectively total eclipses, although one of them's really an annular, from the same spot within a period of 6 months. Just figure the odds of that. I didn't, but I will examine this statement about frequency in just a few minutes. I had to convince myself that they were right about this, and I did. But first, I wanted to see how these two eclipses would look from outer space. And this is one of my favorite acquisitions from one of the NASA websites, the Goddard Space Flight Center. Does everybody see that moving? You see it moving, Mike? Terry? I'm going to let you watch this through a couple of cycles, garner your powers of observation, and then we'll discuss what's going on a little bit deeper. You'll note here that the Earth is not rotating. So I figure this is what you would see from a stationary satellite in synchronous orbit. These animations were done by Dr. Andrew Sinclair, who I did send an email to tell him that I was going to use his animations, but it didn't get through. It got bounced back. So I don't know if he's still with us. But he did some interesting work here. So what you should have noticed is that Smokey, the one on the left, has its moon near the descending node of its orbit. Therefore, the eclipse travels southward, which you see on the left. Bandit on the right has its moon near the ascending node of its orbit, and the eclipse is traveling northward. And did you notice that both eclipses have a general west to east path? And we'll get into that more later. Also, the fact that eclipses nearing the equator slow down and speed up when moving away from the equator. And this is because of the difference in speed of the surface of the Earth versus latitude. Trying to advance my slides here. Okay. This shows the path of the two upcoming eclipses across the United States, and also on this map, the 2017 total eclipse is shown. And closer to home, down below the Texas map, the light shaded bands, two bands that cross each other, indicate where the eclipses can be viewed as either complete annular eclipse in case of 2023, and as a complete total eclipse in 2024. Now, I forget things, so I have to create mnemonics often in order to remember things. And I came up with one for Smokey and the Bandit. I thought of the movie Smokey and the Bandit, and I thought of Cletus the trucker over his CB radio asking the bandit 23 skidoo in a questioning manner to find out if it's high time to hightail it from Sheriff Justice. And Bandit exclaims 10-4. Yes, it is, in response over his CB. So thus I have a memory aid for the year of the first eclipse, 23, and the months of both, 10 for October and 4 for April. I tried to come up with an added memory aid for the specific days of the month, but I failed, unfortunately. Unfortunately. That was so bad I didn't want to put it in print. Okay. Now zooming in a little closer. One must leave Austin and go westward. I'm speaking first of the 2024 total eclipse. Go westward on the line between Eagle Pass, Texas, and Gatesville to maximize the viewing time of totality for the Bandit eclipse. If you get near the center line, you have nearly 4.5 minutes of totality, but only 1 or 2 minutes, depending on where you live in the Austin metro area if you stay at home. And you can note the durations versus distance from the center line in light blue on this graphic. Now from Austin, you cannot see the fullness of Smokey as an annular eclipse at all. It will be a strong partial eclipse as viewed in Austin. You'll have to travel west and south to see full unbroken annularity. Now, one location where you could view both eclipses in full glory and for maximum durations will be in the Lost Maples State Natural Area near the small town of Vanderpool, Texas, southwest of Kerrville. I've never been there, but it is on my radar screen for sure now. And I'm hoping it'll be as beautiful as the pictures are here, especially if we have an early fall in 2023 and an early spring in 2024. Now, here's a bit of trivia for you. In April 2024, the Bandit will cross over near the town of Carbondale, Illinois, which is where the eclipse of 2017 crossed that area also. So they'll be treated for their second total eclipse in less than 7 years. And our friend Kurt Beatty got on the Google Earth with the coordinates of this and sent me this picture of the exact farm site over which the 2017 and the 2024 eclipses will intersect. Now, I would say we've come a long way since those hominids of 1 million BC when we can produce something like this, prediction like this. This slide shows the durations of annularity of Smokey in Kerrville, San Antonio, and Lost Maples. Nearly 5 minutes of annularity in the Lost Maples State Natural Area. And up here in the upper right, you see the partial eclipse that you will see in Austin. And this just reminds me, as you all know, it's not that you need to check the weather before you go. It's better to avoid clouds and have a shorter viewing time than to be under cloud cover at a otherwise more optimal location. It's not just the weather. The chaos during the great eclipse of 2017 should have taught us to plan ahead. I'm considering renting a single family cabin in Los Maples for at least one of the two events, and to get there early and leave late to avoid the mess that's going to happen there. You see what happened in a little town in Oregon of 7,000. They got flocked by 100,000 people. I expect Los Maples will have could have the same situation. I couldn't find many motels in the area. I mean, you can probably book some now in Kerrville, maybe, but then you'll have to deal with the roads driving over there on the day of the event. So I don't know. Okay, I wanted to get a little bit into the modeling work. I spent quite a bit of time doing modeling of eclipses as I studied the Antikythera mechanism, and I now have a detailed model of solar and lunar positioning good for any location on Earth in any particular time, past, present, or future. This method that I used has a claimed accuracy of no worse than 3/1000ths of a degree in zenith or azimuth. So it's quite accurate. I've got this programmed in Excel, and the graphical results that my model produced for the Bandit eclipse are shown here. This location that I chose for this particular graph is on Highway 183, just southeast of Lampasas, Texas. And the eclipse will begin with first contact at a time 1718 universal time. That's 12:18 p.m. local. The elevation will be 60 degrees at that time, the solar elevation, with an azimuth of about 140 degrees. That is towards the southeast. The eclipse will end with final contact 2 hours and 40 minutes later towards the southwest. And you can see the path of the moon as that will occur as in crossing over the sun in the time lapses that I have graphed out here. The midpoint of totality will be at 1837 universal time. That's basically Greenwich Mean Time, or about 1:38 p.m. local time. So early afternoon for the Bandit. Both the sun and the moon will be almost directly due south with a zenith of about 66 degrees. So I went online and checked my results with images I found on timeanddate.com, which is a pretty good site, and found that they had modeled it correctly, because I knew that I had. And this is a close-up detailing totality, again, from my model. I found that I reproduced the 4 minutes and 24 seconds duration of totality to within a second, as reported by NASA. Here is a Google Earth photograph of one of my prime go-to spots, or backup spots anyway, for the Bandit eclipse. This will be a monumental eclipse, so I picked the Lampasas Monuments Company, which is southeast of town on Highway 183, for this picture. And this will be looking in the direction at which the eclipse will occur. That is almost due south. This is an extraterrestrial's cartoon view of the 6-month-long journey of the Earth and the Moon between the two eclipses. Shown is the sun-centered view of the Earth, of the Earth's orbit from October of 2023 through April of 2024. The Earth's orbit passes through winter solstice, Earth at perigee, spring equinox before arriving at the second eclipse. And I've also shown just 2 of the lunar months intervening, just to provide you with a sense of the precessions that are involved between the 2 events. Smokey occurs at new moon on October 14th. And in that new moon, the moon will be near the descending node of the inclined lunar orbit. That's in sub D. My wife just brought me a Kleenex, so I must be sniffling. Sorry about that. Okay, the descending node, which is diametrically opposite the ascending node in sub A, is where the moon is just passing downward through the imaginary plane of Earth's orbit around the sun. Hence, the shadows cast by the moon in passing through the descending node will strike the Earth and result in eclipse, and the eclipse will be moving southward because it's moving from north to south. I also indicate that in October 29th to be exact, there will be a lunar eclipse in that same month. And this is not a coincidence. A lunar eclipse almost always occurs in the same lunar month or in the following lunar month after a solar eclipse. Okay, for the remaining lunar months, focus on the new moons, the solid black circles. The new moon occurrences are progressing counterclockwise from month to month. So you can see that the moon is moving counterclockwise from month to month throughout the orbit. And let's see, lost my place. Okay, sorry. Oh wait, the red P for the April event, the eclipse of Bandit, the P is where the perigee will be of the moon. So the perigee means that the moon is very close to the Earth. It will be large, and that will be a total eclipse. It will cover the sun. On the other hand, Smokey is actually closer to the moon's apogee, and that is a reason why it will be an annular eclipse. It will be smaller in the sky. It will be further away from us. Okay, I want to briefly look at 4 types of eclipses. In a total eclipse, number 1, shown here, the sun is completely obscured and the umbral shadow strikes the Earth over a region with a diameter of 100 to 160 kilometers. The observers in the penumbral shadow of a total eclipse witness a partial eclipse. And the penumbral shadow has a diameter of 6,400 kilometers or more. Now, a non-central eclipse, that is one where the umbra does not strike the Earth, it will be a partial eclipse only on Earth. It will not be a total, only a partial part of the Earth. Now, with an annular eclipse, the moon only partially obscures the sun, and the resulting central shadow on Earth is not as dark, of course. And this shadow is called the antumbra. During an event, some observers at the midpoint of an eclipse path may experience a total eclipse, while others on the center line, that same center line, we'll see an annular eclipse. This is called a hybrid eclipse, and it's a rare event happening only a few times per century on Earth. Okay, this is an example of a NASA eclipse map. You can see these when you go to the NASA website and look up the legend, so you have any questions about what they're trying to depict, they give you an annotations that look like this. Pretty much self-explanatory. A couple of comments. They give you, they report the time of the eclipse is 1827 TD. TD stands for terrestrial dynamic time. And TD is the time astronomers use because it is uniform in time scale. It's based on an atomic clock. Earth time is not a uniform time scale. It is based on Earth completing a day against the background stars. Thus, it depends on the time period of Earth's rotation, which generally is increasing in duration. The Earth is slowing down, the period is increasing. Earth time is reported confusingly to me as universal time, which is basically GMT. So to convert from TD to UT, you must add a correction called delta T. And delta T changes over the years, over the decades and the centuries because of changes in the rotational speed of the Earth. Currently, delta T is about 70 clock seconds. In 1902, it was 0, but now about 70. So the universal time of the eclipse of 2017, of maximum eclipse, would be 1827 less 70 seconds, or about 1826. So it makes a small difference. Eclipse magnitude. They show on the map the limits in brown here, where the magnitude will be 50% rather than 100%, where it will be along the center line. Actually, it can be greater than 100% along the center line if it happens that the moon appears larger in the sky than the sun. NASA also indicates a value of gamma down here in the lower left. This is an indicator of the centrality of the eclipse at its maximum relative to the center line of the Earth at the equator. So a value of, it can range from +1 to -1. And if it's +1 or -1, that means it's just at the poles, the North and South Pole. If it's 0.5, it's right on the equator. So we're fortunate that we can see annular eclipses or eclipses at all, because the size of the moon and the sun are about the same in the sky. A half a degree, as I said earlier, or 30 arc minutes. And this is because the ratio of the two diameters of the sun and the moon, the ratio of those two is about the same as the ratio of their distances from Earth. So each of those ratios is about 400 to 1, which results in the similarity of the sizes. Now, annular eclipses arise, as we said, just sometimes because the apparent size of the moon is just smaller than that of the sun. It doesn't cover it. In fact, at least in the northern hemisphere, I estimate that there should be about 2 annular eclipses for every 1 total eclipse. This is based on the graph I put together and it's shown here. I created this graph to compare the size ranges of the sun and the moon as part of my study of the Antikythera mechanism. And therefore I was using a latitude of Athens, Greece, which is about 38 degrees north. while Austin is about 30 degrees north. Now, a noted Belgian mathematical astronomer, Jean Maes, made more than an estimate. He made a quite detailed statistical study to determine the frequency of total and annular eclipses at any random spot at any given latitude. The results vary significantly by latitude, and we will talk about that on the next slide. But I should have said in this table that this is the occurrence at a random locale versus its specified latitude. So we're talking about you're at a random location at a given latitude. What is the frequency of occurrence of the two types of eclipses? So it turns out that for the Austin area, for our latitude, you would experience a total eclipse one time every 340 years, and an annular eclipse once every 255 years. So, I mean, that's why this is such a rare thing to be happening. And Mr. Maes reports that at our latitudes in Texas, about 57% of eclipses will be annular. How am I doing on time, Terry?
It's 9:30. Oh, 9:36.
When did I start?
About 8:25, maybe 8:30. So
Okay.
you're about an hour in.
I've got an hour in, so I need to speed up. Okay. He reports the frequency, and he gives some good rationale for why you see a different ratio of annular to total in the northern hemisphere, in the southern hemisphere, and at the equator. And there's some good rationale for that, and I'm going to skip over that to get back on track here a little bit. I did want to show you a toy. I built an analog model. Oh, I can't get my screen set right here. I built an approximate analog model in order to verify that statement that there are about 2.4 eclipses of any type on Earth in a year. So in doing that, I built a model that assumes 3 constant rates of movement. The Earth going around the sun in 365.25 days, the length of the lunar orbit, 27.32 days, and the length of rotation of the line of nodes. The line of nodes is where the orbit of the moon intersects the ecliptic. That is, the ecliptic is the orbital plane of the Earth moving around the sun. It's critical that the moon be within about 18 degrees on either side of the ascending or descending node. That is the extremities of the line of nodes in order to see an eclipse. So very simple model, assuming things that are not true. These rates of motion are not constant, but they're close. They're close enough for the following to result. So here's the model I built. It's got the Earth at the center. I've got an odometer counting days, tens of days, hundreds of days, thousands of days. And I've got an icon that's going to be in motion soon for the moon and the sun, and the line of nodes, the ascending node A and the ascending node A and the descending node D. That line is going to move also. Turns out that the motion of the line of nodes is in opposition to the motion of the sun and the moon. So it's going to move in an opposite direction. So here I'm going to, and I've set an initial condition where the moon and the sun are both at the ascending node. So I've set it in motion. Again, this is just an analog model. It's not calculating anything. It's just showing you there that's approximately a new moon where I stopped it because the moon is between the Earth and the sun. And there's another new moon. And there's another one. I'm going to stop it on the first eclipse, solar eclipse that occurs. That's when we get into the pink. And there we are. So at 178 days after where I started it, there will be a solar eclipse somewhere on Earth. Don't know where from this simple model. But I continue doing this and gather data. And as it turns out, I determined that I ran it for 18 years and saw 44 solar eclipses. And that turns out to be 2.4 per year, which is what the references on the internet say. So, okay, I'm gonna move through this very fast. I created a digital version of that same model and looked at the eclipses that NASA is predicting to occur, the next 15 that they're predicting to occur. And with the same simple assumptions that I had on the analog model, I was able to predict all of the NASA eclipses, although I had some errors. Some of them were off a day. And actually I had one false positive indication of an eclipse that will not occur on August 24th, 2025. That eclipse will not occur. So I was pretty happy with that, but improvement is still needed to do anything serious other than just to have fun. So I looked on the internet and found the next level of improvement. And this includes corrections for all of the so-called lunar anomalies. That is, you have to take into account Keplerian orbit, the gravitational influences of the sun. We're talking about a 3-body problem, not a 2-body problem. We talk about the Earth, Moon, Sun system. And it turned out with this improvement, I predicted all 14 of the future NASA eclipses, excluding the one in June, which I used to set the initial conditions for this model, exactly to the day. All 14 of them, no false positives, with an average error of about an hour from time of occurrence. So you can get pretty close with only approximate techniques. I wanted to acknowledge a local physicist, which some of you probably know if he's still at UT. I don't know him, but the methodology that I used for the improvement came from a publication by Richard Fitzpatrick, a professor of physics at UT Austin. So if you know him, pass my compliments along to him. Now for my serious work, where I'm really trying to model things precisely, I use methodology supplied by the National Renewable Energy Laboratory, NREL. In 2008 and 2010, they published 2 articles that explain in detail the methodology that you need step by step, and equations and algorithms to get highly accurate positional models of the sun and the moon. Unfortunately, they don't give you the source code or an Excel spreadsheet, so I had to build that and spend many hours making sure that it agreed with NASA, because I said NASA's was probably better than NREL's, or at least equivalent. And turns out that they were. The advantages of this, of having a detailed model, is that you can put in your location on Earth, your latitude, your longitude, your elevation, and so forth, and you'll see the lunar and solar positioning. Now, if this is not a predictor, you have to know it pretty close to where an eclipse might occur using a simplified model, and then enter dates and times until you get conjunction of the sun and the moon within this detailed model. But from that, then I can generate the graphs of the obscuration time lapses of the sun and the moon exactly, even for eclipses that the ancient Greeks saw 2,500 years ago. I'm going to skip more on Saros cycles. This just explains why there's 18 years, very closely 18 years between successive eclipses. I'll just briefly show that fact with this slide. This shows on the right the Bandit eclipse in April of 2024, and you can see its path in blue, and the three immediate predecessors to Bandit in the same Saros series, the same family. Each of them occurred 18 years apart leading up to Bandit. You'll notice that Bandit looks almost exactly, in terms of longitude, like the eclipse that occurred in 1970, which is in the same family. So that's the 54 years. Every 18 years, the eclipses look alike, but they may show up somewhere else on Earth. But every 54 years, it's highly likely that they will reproduce in the same longitudes. Now here's one for your great grandkids. A successor to Bandit will occur on July 16th of 2186. This will be an equatorial eclipse, and equatorial eclipses are quite long in duration because the Earth is moving faster there, and therefore it can keep up with the movement of the moon a little better, and that leads to longer eclipses near the equator. And that will be the longest duration of totality of any solar eclipse ever, between the years 4000 BCE and the year 6000 to come.
What is the expected length?
Length?
Yeah, what's the duration going to be?
Well, I'm sorry, 7 minutes and 29 seconds.
There it is. Okay.
I'm going to skip that. Okay, I want to quickly go through some things that you can take your kiddos to do, or you can do yourself without sophisticated equipment. It sounds like you guys all have sophisticated equipment and an agenda of what you're going to do during the but I don't, and I tried to brainstorm some things you could do. Actually, some of you probably already done, but simplest thing you can do is record the air temperature. If you're near the center line of an eclipse and it's a dry day particularly, you'll see a pretty noticeable temperature drop, and you could actually record that versus time if you choose the right temperature measurement device. Here the temperature dropped, looks like about 10 degrees Fahrenheit. But you would need a device, not a glass thermometer, but something like I've randomly selected here, a thermistor or something with a time constant around 15 degrees second, 15 seconds. That will be not too fast and not too slow. It will filter out some of the noise in the temperature measurement and be fast enough in response to produce a pretty good graph. You could actually, from a sufficient elevation, which you probably won't find in Vanderpool, but you might find somewhere else, or using a camera drone and get it up in the sky, it's possible to extend your horizon far enough that you can see the passage of the umbra on the ground coming across the landscape. Now it's moving at about 1,600 miles per hour ground speed, and it will be fuzzy. So you have to be at the ready to catch it if that tickles your fancy. And I've shown here a link to a video that I'm not going to take the time to show you now of tips on setting up your camera and editing afterwards to do this. I've shown here a fictional umbra passing over the Martian rover. Actually, there are no umbras on Mars. I think that's my next slide. Yes, here's an actual Martian eclipse seen by rover Curiosity. It's a annular, and they say this is about as big as they come on Mars, and they're very fast. The three photographs there are Phobos, and they're separated by 3 seconds between images as they pass over the sun. Phobos being, I think, 16 kilometers in size. And I forget, it's Deimos, is that the second largest one? Or the second one? It's smaller. And there are sites on the internet where you can build a improved camera obscura, as they call it. We've probably all done the basic pinhole projector with the paper with a pinhole allowing the sun to project this image on another piece of paper, but you can actually build a personal one. Go to exploratorium.edu and they'll show you how to build one to fit over your head. Yeah, about 3. Fit over your head. My wife just came in to show you about 3. So I'm gonna get there. Fit over your head, and that gets the background light out and gives you a better view, they say. Or you can build a desktop version, which this lady in this old lithograph has done with using an old camera lens, not camera lens, telescope lens, and a mirror inside. And if she were to elevate this up towards the event itself, the eclipse, then she could, because of the mirror in here, she could trace the eclipse as it occurred. You could also break out your Crookes radiometer for your kids to use and possibly include a pinhole projection on a video of it in motion as the eclipse plays out. Bigger toys than that include solar collection panels. Here is a response to the Great American Eclipse of 2017 that a Seattle homeowner published, and it shows his power supply in green versus what it was on a day of similar sky clarity a few days before. And he saw a 94% loss in power output during the eclipse. And I went to NASA's website and found out that his graph coincides exactly with the information on the eclipse as NASA published it. They said the obscuration at his particular location was 92%. His watt meter went down 94%, so that's pretty darn close to actually witnessing an eclipse without even going outside your house. My neighbor has an app on his phone where he can see what's going on with his solar collection panels from his sofa. Okay, here's one a little more flamboyant. For Bandit, or for actually for either one of them, consider hiring a business jet to get out just ahead of the Umbra, north of the Rio Grande, along the center path of the eclipse. And if you get a fast enough Learjet or whatever, you can extend your duration of totality from 4.5 minutes to 6.5 minutes, if that is of any interest to you. And maybe one of the airlines will offer excursion trips to allow this to happen. Eclipses always move from west to east, as I said, and that's because the moon is moving faster in its orbit than the Earth is spinning. So, and they're both moving in the same direction. So the eclipse moves from west to east. Now, if anybody's seen the so-called shadow bands, I think Terry has, I would like to hear about them because I just discovered those in my research. I'm about through here, but I find them fascinating, and I'm still trying to understand exactly why they occur. But it turns out that just a couple of minutes before or after totality, when the sliver of when the sun is just a sliver that you can see on a large viewing screen, either on the ground or elevated up to face the eclipse itself, you can start to see some bands, perhaps not with this degree of distinction between them, moving. As you get closer to totality, maybe a half minute to a minute, they get narrower, and the instance before or just after totality, when you're at the thinnest of crescents, you can see very, very narrow band space, and more distinct, it appears, based on, here is some still photos that Dr. Wolfgang Strickling in Germany said that I could show you, of 45 seconds before totality down to 10 seconds before totality, and you can see these bands of alternating either reinforcement or destruction or interference, all caused by, they think, the atmospheric winds moving along packets of air with different temperatures and therefore different refractive indices, which is causing this effect. And I would like to understand it better. There is a YouTube video that I will finish up and open it up for questions, but let me bring up this video and show it to you while you're thinking about what's done. I'm getting managed to stop. I'm getting advice to stop. So I will let you Google shadow bands, and you'll find a YouTube video with this gentleman's name, Paul Wells, and it shows you a very remarkable video of the shadow bands. for an eclipse he witnessed. Terry, I'm done. Thank you for your perseverance. It appears
Oh,
that
sure. We can go ahead and spend a little bit of time on Q&A. I think you've still got a pretty decent sized crowd here. So would anybody like to start off with some questions?
Yeah, I have a question.
Yeah.
So back around, I think, slide 28 or 29, you pointed out that the maximum totality for the 2017 eclipse was right there in southern Illinois, which, if I remember correctly from my planning for that eclipse, was in fact Carbondale, right where the 2024 path crosses. What I'm wondering, is that just a coincidence, or is there more to it than that? Where is the maximum totality for the 2024? Is it also in Carbondale?
No, I'm sorry, I misled you there. I was showing the center lines.
Yes, yeah, I understand that. I understand that, but as I recall from the 2020 or from the 2017 planning, the Carbondale was also the maximum duration of totality for that eclipse.
Yeah, that may be true. I can't speak to that. I know that the maximum duration of totality for the 2024 event will be south of us in Mexico, I think.
Oh, okay.
It'll just be just a few seconds difference.
Yeah.
Again,
Okay.
because of the rotation of the Earth.
I found it an interesting coincidence that the two crossed at the 2017 maximum. I was just wondering if there was more than just a coincidence there.
That I don't know. I haven't studied the 2017 eclipse to know that I don't know that was a maximum. I'll take your word for it. But I know that the maximum for the 2024 is not in the United States.
Okay. Good enough. Thank you.
Okay, anybody else?
Any comments? Anybody seen the shadow bands?
My name is David. I have a question. If I understand correctly, you were saying NASA was computing eclipses, but some of their information was wrong. Could you explain how they got that?
Oh, I totally screwed that up. I was trying to use my simplified approximate model to see how well a very simple model with constant periods of revolution and precession would match the eclipses that NASA has predicted to occur. I accept the fact that they've got that right. And I was saying that my model missed by a full day on 5 of those of the 15. The simple model.
Okay.
The simple model.
I understand.
Okay. It got better as I added consideration of the lunar anomalies into it. And actually, I got it down to missing none of them by the day and actually getting to within an average error of about less than an hour for all of them using a improved but still approximate model that Dr. Fitzpatrick had published. Is he still at UT Austin? He has written extensively on mathematical astronomy. I figured somebody would know it.
So about the shadow bands on the 2017, I'm not sure if it's an actual recollection of seeing them or somebody may have made a video shortly after that of the location we were in, but I recall a building with white siding on it. and we were observing the bands on that. So there were several people with me. They might speak up if they remember seeing those shadow bands. I don't think I dreamed it entirely.
I don't remember it, but that doesn't mean it didn't happen.
Yeah, I remember a lot of people actually had like white bed sheets spread out on the ground to try to watch the shadow bands, at least in Casper.
Cass and I were in Nebraska and we actually saw it on the ground. Saw shadow bands.
My wife is gone, so for those people that are still here, I'm going to attempt to open up that video.
Okay.
Although, have I still got my screen share?
Yes, you do.
Okay. It turns out this video is opening up on my other screen. I should be able to just drag it across. This gentleman gets very excited.
Well, I hope you can get to the relevant parts pretty easy because it looks like it's a 16-minute video.
It'll get there within 2 minutes, I think. I mean, you have to wait for the entire eclipse, and then he does it again at the end. But okay, so he's got this big white sheet, and you can see a person. Listen to him. You hear him?
They're all there. Flying shadow. Very slow. Also, the instance is in all. Never seen them so beautifully. 2 minutes before totality. Incredible. Normally it's only 30 seconds.
Oh, you got it. You got it, boy.
Oh, they're beautiful. Incredible.
Incredible is somewhat of a hyperbole, but it's kind of like looking through a campfire and seeing things flicker on the other side to me. But it gets more coordinated than that towards right as you get right at totality. Now something's happening.
I've never seen them so slow and in different directions. They're going that way. Incredible.
Oh, yeah.
40 seconds to go. 40 seconds.
Yeah, it's normal to the direction of the source.
Look at that. Look at that. Wonderful. Look at that.
Oh, dude, it's happening.
Never seen them so beautifully. But don't make any shadow.
I would judge those to be bands now.
1 second. No shadow, please. No shadow on the screen. 6,
Wow.
5, 4, 3.
Yeah, this is very obvious banding there.
Mm.
Boy, that gets dark.
I remember that.
So is that what stars would look like if you could actually see a shadow from a single star? I mean, that's basically the same effect, right? The twinkling causes
Yeah.
the shadow bands.
Yes, it's the same thing.
That's pretty cool.
It's the same thing, but it can only manifest itself when the dimension of the sliver is very small. Other than that, I think it gets washed out. Of course, it doesn't get washed out with a star since it's so small. When it twinkles.
I suppose it might be worth our while to have a suitable white screen about the size of a bed sheet, large when spread out on the ground, preferably flat and stretched tight.
Well, the altitude of Bandit's going to be what, about 60 degrees. So yeah, flat on the ground would probably work.
Do those happen during annular eclipses or only total eclipses?
I have not heard that addressed, and since I haven't worked out the math yet, that'll probably be one of my exercises to do that. But I say no.
It probably depends on the magnitude of the eclipse, that if it's almost total, the closer to total, the more defined they would be.
Well, every one I've seen reference to was a total eclipse. This occurred right before it or right after the contacts that led to totality. So it's a single, almost linear strip, I think, of sunlight. An annular strip, I have not seen reference to that causing the shadow band. It might. That's a good question.
So one thing I'll point out, you were talking about making a reservation there for Lost Maples. I think